Okay, so today's question is a pretty simple one from round 1011 div 2c. Basically, it's a question on a bit of bitwise knowledge and ad hoc. So I'll just roughly go over the question that is asking, and then we can see how we can tackle it. Basically, the question is a short one. What it says is that you have been given two integers, x and y, and you have to find whether there exists another integer k, which when added to both of these numbers can satisfy this equation, right? So the LHS of the equation says that when you add x plus k plus y plus k, whatever integer you will get, it should be equal to x plus k. Remember, this is the arithmetic addition. Bitwise OR, this is the XOR function, y plus k. If there exists such k, which we can add to x and y, that would satisfy this equation, then we have to print out, I think we have to print out the integer k, or if it's not possible, then we have to print out -1. So that basically that's the question out there. There's nothing else to consider about. So as it's pretty evident, we will have to start from whatever information that is given to us. There is this equation. Okay? So we have to look at this equation and find a starting point. When you look into this equation, you will notice that the LHS part is predominantly basic arithmetic operations that we do, right? Plus, minus, division, multiplication, etc. But the RHS part has one caveat, that is this XOR operation. So basically, why shouldn't we try to simplify it? Okay, that is, either we should just consider the left hand side or the right hand side both as either arithmetic operation or as bitwise operation. So you can go around two ways. One is pretty much formula based, that is, if you know the formula, then you can easily simplify it. So what the formula says is that if you have two integers, say a and b, and if you do a plus b, then that can be represented as a XOR b plus a bitwise AND. This is bitwise AND a and b. Okay, I will repeat again. If you have two integers and you are carrying out addition of them, then you can represent them as a XOR b, whatever integer you will get here, plus a and b. Okay, so if we notice here, we can say this is a, right, and this is b. So a is x plus k, b is y plus k, and as I said, we can write a plus b as a XOR b plus a and b. That would be equal to, here we have a XOR b, a XOR b, and hence the final equation will simplify. This a XOR b would get cancelled, and we will be left with a and b is equal to 0. So basically, this formula, what this formula is saying is, you have to find a k. You have to find such a k by which x plus k bitwise and y plus k will equate to 0. This is one way to reach that conclusion. That is, if you know the formula. But as it's pretty usual that you might not know the formula, and I didn't either, there's one observation-based way, which is interesting part. So again, the basic philosophy is saying that the LHS part is arithmetic, the RHS part has a bitwise thing. If we can find a way to look at how the arithmetic addition operation looks like in terms of bitwise operations, maybe we will be able to make some observations, right? So let's look at here. Here's a table, the basic OR operation, right? 101, 011, 000, 11 is 0. And how does the arithmetic addition operation look in terms of bitwise operation? When we have 1 plus 0, it outputs 1, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and with a carry on the left hand side as 1, right? So let's think then. I mean, uh, what exactly this equation is trying to ask us, right? Let's look at the meaning with some raw test case and see what, in terms of bitwise operation, what this equation is actually telling us. So let's take an example. Okay, let's consider that this is my ith bit. This is the ith bit, and yeah, coming from the right hand side, this will be I plus 1th bit, I plus 1th bit. Suppose there were some bits here, some bits here. We're just focusing on this ith bit, okay? And we have uh, this is our x, this is our y, this is x plus k, this is y plus k. and this is our bit. If you do the XOR operation, we can see that we'll get a 0. But if you do an addition operation, right, just like the equation, we are doing x plus k plus y plus k. This is the RHS part. What what would happen in the RHS part, and this is the LHS part. We are getting a 0 here for XOR, and 1 0 is 1. If we do addition, well, 1 plus 1 would be 0 with a carry. The carry would carry over to the I plus 1th bit, and it would make this one 1 plus 0 plus another one, the carry that we got from the ith bit, would make this one 0 and a carry 1. Okay, I will repeat again, we'll see it again. For XOR operation, for our ith bit, for x plus k and y plus k, 1 and 1 XOR would give us 0, and 1 XOR 0 will give us 1. But same operation in terms of addition, when we are adding x plus k and y plus k, what would happen is 1 plus 1 will give us 0 and a carry of 1. This is the carry of 1. This carry of 1 will go to the I plus 1th bit. Here we have 1 plus 0 plus the carry. That means this will store 0 and send another 1 as a carry. And as you can notice here, the RHS integer that would form, right? This is the RHS part. This is x plus k plus, sorry, this is the LHS part, y plus k, right? And this is the LHS part, that is x plus k plus y plus k. They both won't become equal. They are not equal, as we can clearly see. For this operation, the ith bit would become 0. For this operation, the ith bit will be 0, but this one, I plus 1th bit would be 1, but the LHS I plus 1th bit will be 0. So obviously they won't become equal, right? As we can see here. Let's try some other combinations also, but this should give you some hint that the problem occurs whenever there is a carry, right? Whenever there is a carry, because of this carry, if we didn't have this carry one, right? If we didn't have this carry one, this wouldn't be a problem. But whenever there is a carry, the problem would occur, and you can try it with other combinations too. For example, let's try this combination. Okay, same. This is the XOR. This is the XOR, and this is the addition. 1 1 XOR would give 0, 1 1 XOR would give 0. But when you do 1 plus 1, this would give 0 with a carry of 1, and this 3 1 would give you another one with a carry of 1 here. And again, we can see these both would not be equal. We can try this combination too, where 1 1 would give 0 XOR, 0 0 would give 0 XOR, 1 plus 1 would be 0 with a carry 1, and 0 0 0 1 would again give a 1, due to which it won't become equal. So we can see that whenever there is something like 1 1, this is the problem. This is a no, big no, because of that, there is no way that both of x plus k and y plus k, the LHS and the RHS equation, could become equal. So observation that we can make here is that you want to avoid, you're fine with having 1 0, you're fine with having 0 1, you're fine with having 0 0, but you're not fine with having 1 1, right? As addition, you don't want to have these two values out there. And after writing this, you can easily maybe see it that we want some mechanism, right? If we put this input, we want some filter, some form of filter or logic that identifies if our number x plus k and y plus k, if the ith bit of any of these two, like if the ith bit combination of these two, like let's say here ith, has a 1 1 anywhere in any place, then it would reject it, right? And we can just see it here, as you can see here, 1 and 0 could become 0, 0 and 1 could become 1, 0 and 0 could become 0, 1 and 1 will become 1. So AND operator works perfectly fine here, right? We can use the AND operator to filter out that if like for example, say just for the, I'm taking an example for the ith bit. For ith bit, we would say if, say, I will name it A and I will name it B for convenience. A of I and B of I, right? If A of I and B of I becomes anywhere equal to 1, then that's a problem. It's not possible for us, right? It's not possible. We can't make it both of these x plus k, y plus k, LHS and RHS equation equal. That's not possible for us. That boils down to one possibility that one, if somehow we can make x and y with some k, with some k, we can make sure that x plus k and y plus k is equal to 0. If there is just some k, then yes, it's possible. If we can achieve this one, now our question shifts, compared to the complicated equation we earlier had. Our question shifts from that to this equation, where we want to know if there exists some k by which we can make x plus k and y plus k is equal to 0. If that is possible, then yes, we will just print out that k, and if not, we'll just show minus 1. Now there are two ways to go from here. I would suggest, whenever if you are aware of the properties, you can directly jump to the conclusion. But what you are basically doing is, we have a is equal to x plus k, b is equal to y plus k, and what you're doing is, say you want to shift x by some amount, right, so that it becomes a. You want to shift y by same constant amount so that it becomes b, and you want to make sure that their n is equal to 0, right? So if you would just, if you have already the knowledge of this property, it would be easier. But if you know this table, if you just go out there and see this table, it becomes really easier. As you can see here, say, yeah, this one, just focus on this one. This 4 and with any of this value would give you 0, right? Just see here, this is 0, here it's 0, here is 0 0. So 4 and 3 would be 0, 4 and 2 would be 0, 4 and 1 would be 0. Similarly, 8 would 8 as AND operator with any of the values above it would give 0. We can just notice that here, it will, this part would cancel out everything else, and this will be uh, getting cancelled by this significant bit zeros. So if you can find some way such that you can shift, right, we want to shift either of these x or y, we want to shift it to a power of 2, power of 2, right? They were all power of 2 here. As you can see, the 4, the 8, they were all power of 2. If we can find a way to shift any of this value x or k to the power of 2, then it will become easier for us. We can say that, yeah, such a k exists, and we can print out that k. Pretty much simple. What you can do is just say store mx, which will store the maximum of the two x and y, and you just find the next greater power of 2, next power of 2 of 2, say that is p2. P2 is the power. Just find the difference between p2 minus mx, and that is your answer, right? This is the answer. Now, okay, when is it not possible? When is it not possible to get achieve any of that, right? As I think it's a common knowledge now that if both the values are equal, right? If x equal to y, even if you shift any one of the value, right? If you shift this to nearest power of 2, so for example, it's 3, x is 3 and y is also 3. Even if you make x plus 1 4 and y plus 1 4, both two same numbers, right? 2 and 2 will never be equal to 0. 3 and 3 will never be equal to 0. So it doesn't matter how much amount you will shift it, you can't make them equal. I mean, the end of the both the numbers equal to 0. That's not possible. So you can just write, if x equal to y, just see out minus 1. Else, the find mx is equal to max of x comma y. Find the nearest power. Say p2 is the nearest power, and just we print out answer is p2 minus mx. That's our answer. Much more simpler. I mean, complicated to look at, but a simpler, even easier. My roughly the similar question could be, even if you vary, right? If the question says, instead of k, give me two integers p and q, right? Basically, what the question I'm saying is, say x plus p plus y plus q equal to x plus p xor y plus q. If a question like this comes up, right, where we can shift x by some amount p, and we can shift y by some amount q, say p and q are both are positive, we need to know again same, like x plus p and y plus q is equal to 0. Is it possible? You can do it. Pretty much similar logic. uh, Maybe you can change the question to say the minimum shift amount that you would need on something like that. Pretty much is that's so in a way. Just to summarize the question, the process, thought process, the starting point was pretty much there was only one starting point, this one. From here we saw, so I will summarize it. Simplification, right? The first step would be simplification, because the left hand side was arithmetic operation, the right hand side had some bitwise operation. Why not make everything just straightforward bitwise, or maybe just look at what's happening, right? What's happening, go out there, do some, see what's happening, right? So we took some test cases, we took ith bit and see what's the issue is, what exactly happening underneath the equation. And we found out that whenever there would be a carry, possibility of carry in terms of addition, it's a problem for us. And if we can find a way, if such a case exists due to which a carry won't happen, then we can say that the answer exists. And we just needed a way to filter out, to find out whether a carry exists or not. And we can, if you will write it down, again, as I said, the best possible way would be to keep writing it down. Whatever observations you're making, keep writing them down. And when you would write this 100 100 10 is fine for me, 01 is fine for me, 00 is fine for me, 11 is not fine for me, and I need a filter logic. And it's pretty much evident from here that 10 and operator would do the best job here. And after that, the whole, uh, if you go and look at the table again, same step, that just rough it out, see the right some stuff, and try to look for the pattern or the information or the the knowledge that it's hiding out there, right? If you would just write it down, okay, fine, I need to find a and b is equal to 0. Is it possible to do it? You just write down the bitwise or look for the bitwise form of 1 to 10 number, and you will just notice, okay, anything above 4 and with 4 would give 0, anything above 8 and with 8 would give 0. And that's it. That's the whole thought process. uh, a pretty short code, and that's it.